Hey everybody, my name is Ryan Brooks. I'm a principal technical artist at Epic Games, and I'm going to talk to you guys about some kind of methods that I've been using for doing shaders and environmental effects inside of Unreal Engine for our games and tech demos for a while. So just a quick introduction about me. I actually started as an intern at Epic about 16 years ago now. It says 15, but worked as an LD and an environment artist for about 5 to 10 years and kind of slowly transitioned into tech art by getting more interested in just the technical problem solving and polishing and optimization part of environments. So just to give some insight into my thought process, how I started solving things more intuitively and then slowly kind of gravitated towards solving them properly and mathematically. And this is kind of hopefully give you guys some insight to start thinking and doing things in a similar way. So an overview of this talk, kind of going to go over the concept of analytical simulation. And that's really just the idea of driving behavior with math as opposed to kind of controlling it on the CPU and always taking and updating it for example, like a gravity arc. And that's going to involve doing things on the vertex shaders of materials where possible, and then a lot of ways to modify those effects using information such as distance fields or UV gradients in your materials. So analytical simulation, as I said, is kind of based on modeling behavior using functions, and then finding the right way to define the inputs of those functions using user parameters. And those parameters can be a single scalar or a vector parameter, or some information about the environment, like the distance fields that I mentioned. And this is kind of meant to replace regular simulation where there would be a CPU or ticking cost. You could call it analytical simulation, you could call it implicit behavior, you could call it procedural simulation. It doesn't really matter what you call it, it's more just a way of thinking about things. So some of the benefits of analytical simulation is that it makes it easy to synchronize different effects across your scene, whether it's ocean water or wind and fire and things like that. And it provides a way to make memory cost of these effects easily trackable, as opposed to effects where you have high spawn rates and bursts where the allocation can be hard to track, especially for a heavy action-based game. And we can avoid the ticking cost of actually triggering and doing those things by building in some of our time functions into the shader. And another side benefit is that this stuff can be made entirely deterministic, so you can scrub forwards and backwards and always get the same result. And that's still something that is hard to come by even in recent tools such as Niagara and Cascade inside of Unreal Engine. So backing up a little bit, what exactly is a function when I say that? A function is basically just something that modifies an input. And in the simplest case, we have a function which is just y equals x, which isn't really interesting, but it just describes a linear line. So obviously, if you were to take something like your UV gradient in the shader and plug in like the x gradient, you would just get the x value and use that as a mapping. And the way that that's written out is y equals f of x. And I'll kind of describe what that means, just because it helps to be able to understand in that way. Maybe if you're reading a white paper, you might need to figure out how do you translate that back into some kind of material instruction. So breaking the function down, the f part in f of x is just the function, and that can be anything you want. You don't have to get caught up in actually the terminology at all. And the x inside of the parentheses is just your input. And for most of the demos in this talk, that's going to be time plus some additional little parameters like an offset or a user parameter. And then the y basically just represents the output, but what you do with it is entirely up to you. And it's named y in the mathematical context because people are graphing things across the x and the y-axis. So basically that plots the point on the y-axis. So here's a slightly more practical example, but still really simplistic. We have y equals the sine of x, and that gives us a sine wave, which I'm sure pretty much anyone who's done any effects is pretty familiar with. And usually we'll use something like time for x to get an animated sine wave. And this is actually the foundation for so many countless effects. Just to name a few, like wind, water, earthquake shakes, tension on lines, flapping bird wings, bouncing balls. The list kind of goes on and on. You can use a sine wave as the foundation for pretty much anything. So we're going to go and show a couple really simple examples and then kind of build up to something that you might actually want to put into a scene. Okay, so I mentioned a bouncing ball. That's actually pretty easy. We can modify our function just by adding one new operator, which is the absolute value operator. So when you take the absolute value of the sign of something, you kind of flip the function so it's all positive, and that actually pretty well mimics what you would get if you were to do like the quadratic of the kinematic equations, which I'm not going to go into here because it's not necessary. Most effects artists will tweak something to taste and get it to feel right, rather than stressing about it being 100% physically accurate. So basically, this is a quick example. This is actually from a content example map that comes with the content examples project in Unreal Engine 4 called the Math Hall. And that's actually been included for about 5 years now. It wasn't ever really widely released, but there's a bunch of little slides kind of along the same vein that I'm using in this talk if you guys want to check that out. So here we have y equals the absolute value of the sine of x, and we kind of converted it to a vertex shader using time for x, and we used y as the vertex offset on the mesh. Okay, so you're probably thinking, hopefully it's not just going to show these little math graphs all the talk. So here's what that actually looks like in a material graph in Unreal Engine 4. So writing a vertex shader in UE4 is pretty simple. Materials have an input pin called world position offset, which when you don't hook something up to it, it's just going to be 0 and do nothing. And you can hook up anything from a constant to any function you could think of. So here we're basically just taking the time node, which is the game time, taking the sine of it, then the absolute value, and then multiplying it by that blue color there, which blue is basically just 0 for x, 0 for y, 1 for z, and then it's multiplied by 100, which is the magnitude, which is in this case is just how high is that ball going to jump. And that's the part where you would obviously want to tweak it or maybe apply some additional sideways velocity instead of just blue. Maybe you add a little bit of red and green to that color, and that would make the ball start to jump around sideways with noise. So what if you wanted to control the starting time of that jump rather than just having it always looping and going without actually having to trigger it on the CPU with a timeline or any of those traditional methods? There's a pretty simple way where you just subtract the start time and then tell this material that initial start time when the interaction occurred, and then you just clamp the resulting time to positive values. So the nice thing about that is you kind of have a local linear timeline for when your effect starts, and you can do all the other things we're going to talk about, modifying the curve to be a power or a sine or just about anything. And this is here showing kind of sliding this start time offset and then applying just a power, which is just kind of making it an exponential curve. In terms of applying that to the previous material graph, we don't really have to add much here. We just take in between the time and the sine node, we subtracted start time, and then we did max with 0. And max actually means, take the larger of these two values. I know it's kind of confusing. It works a little backwards from a clamp node that most people are used to. But just know that, yeah, max takes the bigger of 2. It's not basically saying clamp it to 0. It's saying clamp it to above 0. And then the rest is kind of the same. And you can do a lot of stuff with this, from fading out a whole bunch of decal effects without having to then tick them, which I actually used in the past for the Epic Zen demo, which was a mobile demo, because we had all these little splines that you could drag around to draw on the sand. And then we wanted them to kind of smoothly fade out as you drew too many without it looking bad with them popping out. I wasn't able to get a video of that, but I recreated a simple little spawn graph on the left where clicking spawns a decal, which is a mesh, which gives you more flexibility than a decal. So being able to do this by yourself can be nice, and then they all just kind of fade out. So what that looks like is pretty similar to the example before, but instead of a sine wave, we're basically taking this time, subtracting start time, but we're also kind of including the lifetime that we specify and then the fade time. So notice we kind of subtract the start time with the combination of lifetime and spawn time, lifetime and fade time, and then we divide by the fade time, which kind of makes it a 0 to 1 gradient along that desired time range. And then the saturate node after that is a clamp node between 0 to 1. It's actually free, adds no instructions to the shader. So I tend to use a saturate instead of a clamp, and it's also cleaner looking in the graph. The clamp node is big and ugly, and I don't like it. And then the 1 minus x node there is basically just inverting, because we want the time to be, we want the result of this to be 1 until it fades out, rather than being 0 and then going to 1. So it's basically saying, hey, this thing stays on, and then it just fades off. And the material for this little custom decal is fairly simple. This is basically, when I was clicking, it was spawning an actor, and that actor just had a static mesh. And then on begin play, it was just kind of setting itself up once. It creates a material instance dynamic, which in UE4 is our concept of something that you want to modify a parameter on the blueprint. And then we specify what is the spawn time, when did we click and create it, and then we specify what is the lifetime. And that's just to allow you to kind of change it on the blueprint if you wanted to, but you don't have to specify that in the blueprint. And then notice that there's a delay of the lifetime which kicks off a timer, and then it just destroys itself. So the blueprint never has to communicate back to that blueprint to modify it for it to fade out. It just kind of goes. And this can be really useful because you might end up with a lot of different things ticking, and you don't want to show up on some programmer's profiling graph of, hey, what's all this ticking you're doing here? So anytime you can minimize that is going to be helpful. So that same fade out logic can be modified instead of being a fade to be a behavior on the vertex shader. And again, this is just a very simple permutation of that prior example where we take that timed graph or that timed function and then apply it with a sine wave so that our little cube kind of just jumps up on click and falls. So these are just vertex shaders. There's no ticking or animation involved. And the way that that works is fairly straightforward. Just like before, we take time, we subtract spawn time. This time we renamed the lifetime as air time because we say, hey, here's how long we want this little cube to jump up and before it falls down. And then saturate is a clamp. The only thing that's really kind of not obvious here is that the sine node had its period changed to 2. And that's just because sine kind of goes both positive and negative when you have a period of 1. So by having the period of 2 and clamping the input to 1, we just kind of stop time before the value goes negative, which makes the cube just kind of rest right on the floor at the end. And another quick note, in UE4, the sine node has a default period of 1, which is really confusing to a lot of people because in traditional mathematics, sine has a period of 2 pi. So that's just something to watch out for as you're reading and digesting a white paper that has sine. You'll just need to multiply or divide your period by 2 pi or just enter the period that you want directly in the sine node. And as before, we just multiply by the z-axis, and now we have a jump height parameter, which is kind of where you would decide how much velocity, how high you would want it to go. And so another thing that we can kind of add to this to get even more useful behavior is a scaling by life trick on the vertex shader. So here on the right, we see a static mesh with the vertex shader applied, and I'm scaling the scale parameter from 0 up to above 1 to scale it up. And the way that this actually works is if you take, in the vertex shader, if you were just to plug in negative world position, which would be 0 minus world position, that would collapse all the verts to 0, or the origin. But you can also get an effect where you can smoothly scale to some other point rather than the origin by instead of saying 0 minus world position, you say center point minus world position, and then that collapses to there. And then you can further multiply that scale factor by a scalar parameter, which if you don't invert the parameter like I'm doing here with the 1 minus, then you would probably call the parameter collapse, and 1 would be fully collapsed. And negative scale would actually make it bigger. So I do invert here because that's not really intuitive, and you want a scale of 0 to be collapsed and a scale of over 1 to make it bigger. But of course, that's entirely up to you. You don't have to follow things exactly as I put them in here. Oop. So here's kind of combining the behaviors of the previous examples. Now we have a little cube that jumps up when we click, and then it scales away smoothly, and then it auto-destroys itself when it's done scaling. And again, we don't have any sort of behavior being done on the CPU other than that initial seed that's going on. And so to combine those two things, we're pretty literally just adding the previous graphs from before. You notice we have the little scale by center down at the bottom right. And then the scale by life timing, it accounts for the time of the sine wave jump so that the scale happens right after that just by kind of, we subtract the air time and the spawn time, and then we do the same max and then divide by fade time and saturate, which you'll notice that's probably a common theme in this talk. We always kind of do that. So when you want a looping effect, maybe you don't want something that just happens once, but you have, say, an environmental effect where you want something to happen over and over again. And maybe you want it to be deterministic. The way most people will do that is by using frac. Or you can also use fmod, but I'm focusing on frac here, which is kind of the same thing. It just repeats over the domain of 0 to 1, and it gives you the fractional part. So what that does when you give it something like time, you can think of it as a whole bunch of sequential little 0 to 1 lifetimes. And then, of course, you can perform offsets, randomizations, or any other math on that little slice of time as we have done before. And then this is a useful trick that I suggest for debugging or when you need to go into some kind of manual time dilation mode where you have to scrub with sequencer or something. When you have just time going and looping, it can be really hard to evaluate the behavior at a certain point in time because you say, oh, I have some weird artifact or pop that happens at the beginning or end, but you're not sure where. The way to really debug that is to have a blend where you switch between a time and a manual time using an alpha. And that alpha you'll either set to be 0 or 1. And then when you set it to 1, then you can now scrub the manual time and set it to exact points just for the purpose of debugging. Or if you wanted to, say, control a whole scene with sequencer, you would hook up sequencer to drive a material parameter collection value and then just place those time and manual time alphas in all your shaders, and then you could just in one place scrub it all and drive the whole scene. And we'll actually show an example of that a bit later. So for randomization, there's pretty countless ways of approaching this. Some people just build randomization into their mesh with vertex colors, and that is definitely one way. Another way is to just build linear indices into your mesh, like 0, 1, 2, 3, up to as many things as you want, and then convert that into a nice randomization in the material graph, and it's pretty efficient to do. So we have this node in UE4 called the vector noise node, which has a bunch of cool modes. I'm calling attention here to the cell noise mode, which basically it's defined as a random value per unit of input. And what that basically means is, for any value between 0 and 1, we get a random vector 3, a random color between 0 and 1. So here I took the UVs of a polygon, which is 0 to 1, multiplied it by 4, and then appended a 1 because it expects a 3D input. And you see that gives us a little 4x4 grid of random colors. And that could be useful for a whole bunch of stuff, which we'll get into. So the way that you kind of would want to set that up is on the mesh side, you have vertex colors. So it's important to note that vertex colors are actually stored as 8-bit values. And that means what you really are writing when you modify a vertex color in Max or something else, and then importing it into a game engine, is you're writing values between 0 and 255. Although this may not be obvious to most users because the values are actually appearing normalized between 0 and 1 in both Max and Maya or the Unreal editor. So you actually have to know how to encode and decode that if you want to actually have access to each discrete integer value. If you just start writing random noise that's like from a script, chances are you might write double values or something like that. So what you want to write is values in the 1 out of 55 increment. So you could literally write the math for 1 out of 255 and then put that in as a color. So to read it back, you multiply the color by 255, and that would restore the integer that you had. And so the way this is being demonstrated here is we have a static mesh with 16 quads, and each one has a different integer for the vertex red color value. So one caveat here is that if you just kind of were to take the vertex color and multiply it by 255 and sample it with vector noise, you might get that weird looking precision Z-fighting artifact on the left. And because what's happening there is we're kind of sampling each of those little random squares from before in the very corner, and the GPU has some trouble deciding which side it's on. So a fix there is after you multiply by 255, you add 0.5, and that moves the sample point to being in the center of each one of those little grid cells. And you could also add like 0.01 or something, but it's better to be safe and add the best value that gives you like the furthest distance from the edges. Why not be correct if you can? And that gives you, perfect colors where every card will have a different random value guaranteed. So this is a quick video of putting all those behaviors together. I'm going to go ahead and play it. And this is using an effect that was kind of built for the VR editor demo that Epic showed at its keynote 2 years ago. And originally, we had planned to show sequencer off in a bigger way during this demo, which we kind of did, but had to reduce it for time. So we had these bird flapping effects, and we wanted to be able to scrub back and forth and see the birds fly forward and backwards in time with the ocean. Unfortunately, that never actually got shown during that demo, so you guys get to see it here today and how it was set up. So here we have that same vertex color multiplied by 255, and then we have the cell vector noise. And so the first thing that we're going to do is multiply it by a parameter for bounds. So we took that and noticed that because the noise is actually RGB, if we scale the z-axis, and then the y-axis, and then the x-axis of our offset, we're actually able to control the bounds. And the transform from local to world means you can rotate the actor, and these particles or meshes will actually scale with it. Multiplying that random value before we take it into the offset is kind of like a seed that just jitters the positions. The randomization is achieved, here's that manual time, is achieved by doing the frac and then kind of multiplying it by a travel direction, which in this case is the red axis. So I multiply it by the color red transformed into local space. And then right now without random offset, all the polygons are going together. But then as we add in some random offset, it starts to kind of offset the phase so that these things all loop independently. And you'll notice that before I had my random offset as large as my looping time, it wasn't enough to actually make the randomization fill the entire gap. So you have to use a pretty large number there. And then you can also add in the scale by life, which I showed before, which is kind of being done with a sphere mask here, where you have a sphere at 0.5 center with a 0.5 radius, and then the hardness of the sphere mask is deciding how quickly to fade in and out at the end. So now we have kind of a whole system of particles that's looping and going back and forth, and then we can replace it with a bird mesh. And this was actually a bird mesh that was made by Josh Marlowe for the Zen demo that I showed before, and the vertex animation for the bird was done by Nick Donaldson. But you'll notice I can scrub back and forth, and then the birds go backwards and forwards, and it's always going to be the same deterministic result, which is kind of cool. So we also have some examples where effects artists will use these kind of methods built in with other effects, just to show that it doesn't always have to be an all or nothing approach where you say, oh, I'm going to just do meshes on the vertex shader only. Sometimes we have artists who will do that because there's a missing feature or for some sort of performance reason. So here's an example with a Fortnite emote, which was originally actually a Paragon emote made by Scott Kennedy, who's actually a lead effects artist on Fortnite now, where this heart spawn shape, the heart effect at the end was entirely made as a mesh vertex shader effect. So the way that that works is the heart is a static mesh, and here's the wireframe. It looks like dots because they're really, really tiny polygons. And each of the polygons has a random vertex color to start with. And then the vertex shader is responsible for taking that and randomizing it with a little bit of jittering and a little bit of scaling by life, like we showed before. And because this was kind of built in to supplement an existing effect, Cascade was actually driving the timing of that with a parameter. So it's not using that whole built-in time with the subtracting time. Because if you're building this onto another effect, you might as well take advantage of what you already have going there. So some of the things that are happening here. This uses a material function called sprite, which it's aptly named. It makes your little quads into sprites. And notice here we have the world position specifying the center location. And that works here because the polygons are so tiny to start with. It actually does introduce a tiny bit of error on the camera facing. It might slightly skew them to not be perfect squares, but because they're so small, nobody's going to notice. Although if you really needed to account for that, you would probably use a script like Pivot Painter to encode the exact center positions of these points. And then by scrubbing the size, we're able to kind of change the size of these dynamically in the shader. And then they would camera face as you rotated, which I realize now I should have swung the camera around in this GIF, but just imagine it. So positional jittering is where we want to add in a little bit of chaos or motion. It's kind of like you would get normally from Cascade if you had some random value and use that as a force. So this was achieved here kind of with a little bit of pre-baking from Scott Kennedy, who made the effect. When he actually made this, it was, I think, a spline that he made in Maya, and then he emitted particles from that. And the vertex normal is actually storing the distance, the vector to the spline. And the way that that's working here is because when he emitted those, they're actually facing away from the spline. So the sprites, the little tiny squares, they're actually oriented towards the spline already if you were to zoom in on them, which they're so small that I couldn't really do. But so when you access the vertex normal and just apply a magnitude to that, it pushes it further away, further or inward from the heart shape. And then using that random vertex color from before, some of them move further and some of them don't move quite as much. So to combine that into an actual shader, this is really all it was. We combined the vertex scale with the sprite function, and then we add them together. And then the only other difference here is that we replaced the scalar parameters from before with a dynamic parameter, which is something that both Cascade and Niagara can drive. And again, it's because there's already an effect here, driving the other little sparks that happen. And we have a budget already in place for character effects, so they don't have any really strong, compelling reason to reinvent the wheel to drive that. But we will get into cases where we do exactly that in a little bit. Here's another example by another effects artist in Fortnite, Frederick Sehausen. This is the llama firework that was used for the Marshmallow concert. And again, they didn't have a simple way at the time to spawn these particles in the shape of a mesh. So of course, what most effects artists will do is make a mesh ahead of time and then drive it with some kind of parameters, which in here is pretty much the exact as the previous example for setup, so we don't need to go into that, but just thought it was cool to demonstrate that there's a lot of different effects that can make use of these methods. So another way that we use this, and this is much more common in Fortnite, is for simple environmental effects like fog sheets and dust motes. And the reason we do that is because at this point in Fortnite's development, we actually have zero budget for environmental effects. It's just not even on the sheet, and we're still over budget even without that stuff. So there's a few times where they've added traditional effects, and then it actually does show up in profiling, and they say, hey, why is this here? Can you find some cheaper way to do it? And that's exactly what they do. So on the left here with those big wobbling sprites, kind of same as before, it's a little single static mesh with 5 cards. and then the vertex shader is controlling the size with a sprite, and the guys made a little blueprint that just sets some material parameter values for how fast the sine wave moves it around, what the bounds of it are, and how big they are, and that sort of thing. And then on the right, same thing, but with a dust mote. And again, that's some artist made a mesh that has maybe 100 or so little quads. And then in the material, they set how big they want these to be, how bright they need to be, and that sort of thing. And then they're able to be pretty liberal with how they splat these things around little levels, because Fortnite is made of lots of different individual maps for each building, which makes it really hard when you're authoring these maps to know what is the cost going to be once it's combined with who knows what next to it. So having a cheap way to just splat effects around without being stressed about getting a callback about the performance is pretty important. And then another example that we use a lot for effects is spline thicken. And this is kind of like sprites, but instead of projecting just from the center, it projects along a spline. And here's an example of how that's made. You basically make really thin geometry in Max or Maya or whatever DCC, and then the shader kind of expands that out using the correct camera math, and then it builds normals that are pretty accurate. This was actually a technique developed by Jordan Walker, who is now a art director on Fortnite, and it was for the Samaritan demo in UE3 actually as a part of an R&D. I did some work to make the world normals very accurate to where you can't tell them apart from real normals, and then there's a little example there. So in Fortnite, we use that on a lot of things, like Thomas Browett made a whole bunch of bullet tracers that use that so that they're completely perfectly connected to the beginning and end. There was a little bit of problems with regular tracers getting that perfect contact from the gun to the hit point. So they build bullet tracers, and things like the grappling effect is built with spline thicken. And then we also sometimes build environmental assets, like this whole little coral is a coral that I made where it was procedurally grown with a blueprint and just made these really thin splines. But you can see it's really hard to tell the artifacts. You can almost not tell that it's all fake geometry. I thought the GIF went to a wireframe at some point. Did I miss it? Maybe I showed the wrong one. Well, this next slide shows an example where spline thicken is used on trees. We build these little fronds, which are just kind of a collection of those little splines, like that pipe example. But you can kind of flesh that out and make a pretty convincing, detailed branch that's a lot cheaper by using that. The material function itself looks a little bit daunting, but you really don't need to use most of those inputs. The biggest ones you really want to specify are the thickness parameters, and that will usually vary from the base to the tip using the UV-Y gradient or X, depending on which option you choose to project along. And there's options for adding a normal map and how you want to transform that normal map. And then just as a kind of ode to someone else who's working on systems a lot like this, the Coalition has been building their environmental and game effects like this. There's a little clip here from Gears of War 4 where pretty much all the environmental wind and fire and lightning effects were built using environmental vertex shaders. And I kind of sat down and was hanging out with Colin Penny from the Coalition, over the last few years, and he's been telling me about this. And they're actually going even further this direction for Gears of War 5, and they've authored a system called the Swift Particle System, which allows the artist to kind of work with little modular functions, but kind of do the same types of things that I'm talking about here. And they really did that for the reasons I also outlined, which is kind of interesting to talk to them and oh, you do that for that reason? That's why we do that. And so cool, we have that in common. It's because they didn't want surprise costs when they have a really heavy action firefight all of a sudden. And it was showing up as variable memory cost, whereas when they just build these environmental things ahead of time, you just know when you look at the primitive stats tab how many vertices and polygons are going towards your effects, and right away, it's just easier to track. And they have a guy, James Sharp, who has been working on that. And the other thing that they were trying to combat, which was unique to them, was the cost of spawning particles was really high on the CPU, even for GPU particles. So they just didn't want to pay any spawning cost at all. And there's the video. So yeah, pretty intense amount of dust and wind and lightning and stuff, and it's pretty much mostly mesh-based, which I find pretty impressive and interesting. And in the past, we've done similar things, like with rain. It's usually cards of really thin sheets and things like that. And it can work out really well. Okay, so what if we want to take what we've talked about so far and add some kind of spatial information, whether that's reacting to proximity to something or a looping period that is meant to be synchronized with something else. And so a good example to demonstrate that is with Gerstner waves and water effects. So a Gerstner wave, I think most people are familiar with. It's a way to model the ocean or any water by summing up a bunch of different sine waves. And here is the simple formula, or slightly simplified formula for a Gerstner wave on the vertex shader. Basically, you have its cosine, which is the same as sine, but slightly offset. And you have a wave direction, which does a dot product with the world position, which kind of gives you a linear gradient in some direction. And then you subtract frequency times time, which gives you the animation portion of this. And then it just gets multiplied by amplitude. What I'm not showing here is there's a second formula for getting the wave steepening, which gives those sharp crests. But there's a bonus slide at the end that does include all the necessary graph logic for that. But I wanted to keep it a little bit more streamlined for the main presentation. So here is the material graph for just that z offset part. It's not terribly important right now that you understand every little part of this, but there's logic in here to make the wavelength, or sorry, the wave direction parameter has this speed that's based off of 2 pi divided by the wavelength, and that is the kind of the wave dispersion formula for deep ocean water. Something that you can learn by reading Jerry Tessendorf's paper, but also you don't have to be mathematically correct there. You can just use as a user parameter for your waves as well, and it will probably look just as good, assuming that you take the time to tweak that to taste. So if we want things like synchronized tickless splashes, what we end up using is that same frac function we mentioned before, but what we'll need to do is kind of modify and divide our time so that that looping period matches the frequency of the largest wave. Or if you want to get really fancy, maybe you pick the largest 2 waves of your Gerstner wave simulation. And so what we're really looking at there is to match the function of the frac with the wave period, and then we can modify it from there, like with the power tweak or the gravity arc with sine wave. And what we want is the particles that kind of detect the wave is near them to kind of jump up and have some kind of splash-like behavior. And at that point, it gets really similar to the previous example with the jumping up and scaling, where you'd possibly fade it up and down. And really the only part that you need to solve here that's different, other than dividing by the frequency for the frac, is to kind of figure out how far between wave crests your current position is with time at 0. So basically say, hey, what's the phase offset of this particle? And then once you add that in, you've pretty much solved it. So here's an example. People have probably seen this on YouTube, but I didn't have time to capture a better video for this. But all of this ocean is just static meshes for the ocean and for the particles. They're all just little meshes sitting there waiting for that wave. And then they jump up, they move forward a little bit, and then they kind of reset. So they're always fading back down to 0 before the wave hits, you'll notice. That's because they had to in this scene. I didn't really have a good way to have 2 of each particle. That would have been kind of expensive. There's some other little things going on here, such as making foam fall off the rocks by also sampling that same repeating frac function on the materials for the rocks, and they automatically know how to time based on their object center. Although sometimes you have to apply a little user offset because the wave is kind of more noticeable on the front. So you say, hey, sample a little bit toward the wave, and you kind of set that amount based off the mesh, right? Like if the mesh has huge bounds, but most of the bounds are underwater, you might need to push back that center point, from the visual center above water, as an example. Okay, so I mentioned distance fields early on, and this is where we finally get to talk about how they're used in that previous scene. Distance fields are a thing that tells you how far you are from the closest surface in any direction. And there's a whole bunch of ways to use them in analytical simulation, and just to use them in static materials, such as in the previous example, we are getting the distance from the rocks for the foam, and that part isn't even animated, but because the surface animates, it looks animated. So to describe what we really want to do there on the simulation side, I added one new term to that Gerstner formula here, which is plus phase. And that's actually always in the equation when you look at it in a white paper from, say, Jerry Tessendorf. But you can just default phase to 0 and drop it out. But usually when you start adding in a whole bunch of waves, people will put a random phase per wave just to ensure that you don't have a whole bunch of stacked crests at the origin, which actually can happen and look kind of weird. So phase obviously here is just being shown on the bottom right is just shifting that wave forward a little bit. You can think of it as the starting offset with a time of 0. So phase offset is usually going to be just a scalar parameter, which is a constant for each wave, but it doesn't necessarily have to be. It can be a field as well, and it can be variable. So here is kind of the concept that I'm demonstrating, where we have that same Gerstner wave in orange, which is just linear and hasn't been modified. And then we have some obstacle like a rock, which is that white circle. And notice that the blue wave has been kind of pushed back a little bit, but just near the circle, not the whole wave. And what this is attempting to do is kind of model the effective resistance on the ocean from the rock. And that would happen because, as we know, fluids are incompressible. So if you try to flow into a rock, it's going to apply some pressure back, and it's going to delay the wave and have to make it flow sideways a little bit instead, which will take a little bit of time. So you kind of want to delay that wave a little bit before it hits. So building up to the way that we do that, here we have a distance field being shown on a little water surface. And this is if you just take the node distance to nearest surface with world position. And right here, I'm just multiplying it by a tiny red value because these are in world units, which means the value can get really HDR, and it's pretty much just going to clamp to white if I sampled it raw. So this is to show that there's some distance here. And it's worth noting that that distance is also kind of clamped by a world setting in Unreal. I forget exactly what it's called, but if you type distance, it's distance field max trace distance or something like that. So there is some cost to increasing that. That's something you should definitely check on your project before you just go setting it massive. So of course, the first thing that we need to do to make use of this is to remap that into a linear range of the desired width. So what we do there is we take that distance to surface world value, divide it by distance field length, which is a user parameter, and then saturate and invert it. And then that gives us a nice gradient that's 1 at some surface, and then 0 at the specified gradient away. And here's an example where we have our wave, and I'm kind of scrubbing the parameter for the phase offset. And you can see with a small value there, it really just kind of makes the wave kind of stick to the rock a tiny bit. With really large values, it does weird things, and it actually starts to pull waves back in time towards itself, makes these concentric circles. Maybe someone here will find a way to use that to a purposeful artistic effect. Who knows? So here's actually the graph for doing that lag delay. It's the same as before. We just took that value. I added a power here, which means it does it a little bit. There's an exponential curve that says, hey, the effect gets stronger exponentially towards the surface rather than just linear. And then you multiply it by the distance field phase offset amount. And then you just subtract that result from time. And again, you probably want to keep that amount pretty small relative to the frequency of the wave. Otherwise, you start to, once your offset is greater than the frequency of the wave, it starts to pull in multiple waves, and that's not something you probably want. So by combining the gradient of the distance field with the wave direction, we can enhance the modeling even a little bit more and say, we want to spawn the splashes on the front of the rock, and we want the splashes to be, happen sooner there, maybe be a little bit more opaque there, or we want the foam in the material to be a little bit stronger there. There's really countless ways that you start to use that. So this is what the distance field gradient looks like. We have a node for that in UE4. The way this is calculated is kind of like a normal map. You take offsets in each direction, and that gives you the magnitude of the offset in each direction. So this is actually not normalized by default, but it's pretty common to just normalize it before you use it. But really, that's kind of up to you. So if you do a dot product between that gradient and another vector, that shows you where the vector aligns with the distance field gradient, which you can see here. I'm able to see what's the front side and what's the back side. And if both vectors are normalized before the dot product, that actually gives you an output in the range of -1 to 1. So -1 would kind of be the backside of the flow, which you could use for turbulence, or to extend the wake to be a little bit longer behind the back, or to say the front wake should be a little bit more compressed and stick right to the rock, for example. That's how you would start that. So this same kind of effect can be used for flow maps. I think probably you don't need to go too much into how flow maps work, but they're an artistic effect that kind of distills the essence of fluid flow into a shader. And really what you do is you take two textures and you pan them, or actually advect them by a field. And then because you get a lot of texture stretching once you've advected something or distorted the UVs with some other texture, what they do is they reset and then they fade to another texture kind of with an offset phase. So you see here there's two sine waves, or one is a cosine wave and one is a sine wave because they have the right offset. And then using the absolute value of that, it's kind of fading between texture 1 and texture 2. So you'll notice that when the blue little region becomes 0, that's when the yellow region becomes 1, and they kind of overlap nicely. UE4's flow map node actually uses a linear triangle wave, not a sine wave. I don't think it's a really particular distinction. It's not really noticeable, but it's easier to make a sine wave in terms of writing the math because you don't have to do the math for a triangle wave. Although the triangle wave might be slightly cheaper if you really want to get down into the nitty-gritty, but no promises. So it's worth noting here that distance fields and normal maps can both do this same thing. And in fact, distance fields are significantly more expensive on most modern hardware and consoles. So we don't honestly use the distance fields very much because we might not be able to support it on all platforms. But here's an example where the same exact thing was done by using a normal map of the rocks. And this is an effect in the Fortnite map that I added some polish to many, many years ago. I won't say how long because Fortnite's been in development for a really long time. So what was done here is that the rocks already had a normal map, but we wanted the water to kind of look like it was parting around the rocks and making a little turbulent wake behind them. So that was done by taking that rock normal map and really blurring it and duplicating it and overlaying it on top of itself a bunch of times in Photoshop. And that kind of dilated the shape of the rocks a little bit. And then we added that normal map into the flow map vector a little bit. And you'll notice on the left, I kind of show that normal map, and it gets kind of black towards the middle. That's an example of a UV gradient where the UVs of the mesh, which range from 0 to 1 horizontally, it was just a sphere mask where you say, give me a sphere of, the center is at 0.5, the radius is at 0.5, and then you say what hardness you want, or maybe a power or something else. So the effect kind of smoothly dissipates as the river gets deeper. And the reason that this actually shows a hard edge here is because this material was, I believe, set to masked, and it had another material that was matching the gravel, so we could nicely transition to a cheaper opaque shoreline edge. So here is an example of basically taking that same flow map modification using the distance fields. It gets a little bit stretchy in one part of the animation because of what I'm actually doing here is scrubbing the width of that distance field gradient. So you'll notice there are moments where it looks good and there are moments where it looks a little bit stretchy. That's one of those things where the magnitude of the offset you're adding kind of has to be tweaked a little bit with the radius of your distance field. And then there's also something you can do to kind of improve it, which is kind of detect which part of the distance field is facing into the flow and add a little bit of extra kind of forward compression. I didn't have time to make a separate image for this, but really you could tweak that independently. And then the slide coming up next does show it. So on the bottom is kind of the distance field gradient being multiplied by that linear alpha that we extracted from the regular distance field. And then we're just multiplying that by a parameter and adding it to our flow value. But you notice kind of right in the middle vertically there's a dot product that's being done with the distance field gradient and the flow vector. And then that basically tells us that gradient of how much in the flow we are. And then that's a second, what did I call that? The forward flow adjust. And then that's another parameter you can tweak separately, which is going to kind of push the water forward or backwards at the front of the rock more so than at the sides to kind of help compensate for some of that stretching you might get. And there's a lot of ways to do this. You can add it to the flow vector like I'm doing here, or you can actually add this offset directly into the UVs, which is kind of like warping the UVs, which is something I've done in the past as well, just modifying the UVs of a river to give it some interesting distortion. Really a similar effect. So wrapping up, we've kind of gone over different concepts of analytical simulation, and hopefully you think of it as an interesting method to consider for your effects, and how it's great for environmental effects, and especially to synchronize your different materials across your scene. And it can be a great cost savings if you have, say, an undetermined effects budget. Maybe you have tons of characters, but then they're still asking you to go in and put in a bunch of environmental effects, but it's too late for a whole bunch of new performance profiling, and you need to be just extra careful. You can start to build that way. And more than anything, I want people to consider this as a useful way to begin thinking about effects and to start, thinking that when we describe these intuitive behaviors, that there's often a very solid mathematical foundation behind it. You might not have to define it, but it's still there. But knowing about it can help you spot those opportunities in other techniques, other papers, other talks, and start to apply it in your own project. Thank you guys for listening. And then actually, I promised a couple bonus slides. I actually have 4 to go over really quick, and then we might have a few minutes for some questions. So this is references that I mentioned, Simulating Ocean Water by Jerry Tessendorf. Flow visualization using living textures, kind of like the first mention of flow maps that was kind of used by Valve when they talked about their flow maps a while ago. I actually meant to reference Valve at one point, and someone went, hey, there's actually an earlier paper you could reference. And I was like, oh, cool. And then GPU gems, chapter 1 actually goes into the Gerstner wave derivation pretty well. So it's a great way if you find Jerry's paper a little bit too mathy, just use that instead. This is the full graph for the Gerstner wave. So in the middle, in the cyan comment box, that's the graph we already saw for the Z displacement. The very bottom is the graph for the steepening, which is kind of the horizontal displacement, which creates the sharp wave crests. And then the top is the normals, and those get added together. One note is that there's a little 1 minus on the Z component, the blue. That 1 minus actually happens after you sum up all your waves, not per wave. So if you add them up, you would pull that out of here and do that at the end. And that's because, a whole bunch of 0 magnitude of Z vectors would be basically just pointing straight up, and you want that to be a value of 1. Here's another really useful one that I kind of worked on for that VR beach scene, and this is a lagged wave. So this is if you have, say, something like a crashing wave on the shore, and it has foam that needs to crest up and then slowly glide back down. You want to be able to tweak how far up it slides and control the speed of the rise and the fall independently. So this gives you a nice way to do that. Another thing that I meant to include here but didn't have time to make a good example is curl noise. The vector noise node I mentioned previously has another little submode in there called purling curl. And this is basically a divergence-free vector field based on Perlin noise. And it's great for just adding chaotic noise to things. We have curl noise in Niagara now, which is really awesome. You can add low turbulence wake behind something on the back of the flow. There's a great extra reading here if you have time for how to analytically model curl noise to give you fairly accurate fluid simulation turbulence. And then another concept that I called out during that video with the looping, the ocean, is that the rocks had this kind of falling foam. That was a technique that was similar to flow maps, but instead of providing a vector, it was actually scaling the texture by a point, which there in UE4 we have this node called scale UVs by center. All that really does is you subtract by the center, you multiply it by something, and then you add the center back. And this kind of goes inside of the flow map function and replaces this standard advection. And it's kind of like the fluid is falling from the center, and it's always kind of scaling down, which creates a pretty convincing illusion. And that's it for me, and I'm announcing the next talk. Thank you, guys. I just noticed we actually have a few moments for questions before the next one, so if anyone wants to come up to the mic, feel free.
Thank you. It was a really interesting talk. I had some question. If on a project that doesn't use distance fields for performance reason, would you have another solution for basically bringing those kind of information in the world just maybe by hand, like the most effective one? I don't know.
Yes, absolutely. So that's a very good point. Not all projects are going to be able to afford distance fields for various reasons. You can either just hand paint it, or there's actually a method in Photoshop to be able to take an alpha mask, just a 0 to 1, or a hard edge mask, and convert it to a distance field. Mm-hmm. I actually have a blog about that on my website, shaderbits.com/blog. And there's a distance field technique blog that mentions Photoshop. It's a layer effect. I can't remember exactly how to get it. It was taught to me by John Lindquist, who's another tech artist at Epic. And it's so obscure and hard to find that both of us ask each other like once every 2 years, hey, where was that thing again? So definitely refer to my blog, but it's a layer style that dilates. And short of that, what I've actually done in some cases is use a scene capture actor just pointed at the ground to capture the result of the distance field and then bake it out. Like for that beach scene, for example, with the birds, there's some waves with the rocks poking out, and there was some foam there. That was actually kind of pre-computed by using a scene capture pointing down and making a material that's just black with the white gradient, and then you just capture that, save it off, map it to your scene. And then short of that, the texture-based methods using normal maps that I was mentioning before tend to be more accessible and tend to be more shippable. Like that material makes it down to most platforms on Fortnite. Not mobile. We just use the regular default flow vector on mobile, but other than that, it's pretty performant.
Okay.
Thank you.
Hi there, thanks for the talk. If you have vertex offset pushing something outside the bounds of the original mesh, do you have any special trick to avoid frostum culling going wrong there?
Yes, that's a very good point. I should have mentioned that. What we have in Unreal Engine 4 is a setting on a static mesh object in the content browser called positive and negative bounds extension. So before this, what we had to resort to is the bound scale on the actor in the world, which was kind of bad because it would scale in all directions. And if you had something like a flat card that was flat on Z, no amount of bound scale would make that thing taller, which was really frustrating. So now with a positive and negative bounds extension, you can make that original bounding box whatever uniform or non-uniform shape you want. And then the bound scale still works as a nice linear scale from there if you want to just make a quick last-minute adjustment. But yes, do be careful with bounds because when you make them really big, you always render them potentially, and you need to be really careful with that. So yeah, thank you for that question.
Thank you.
All right. So you were using the animation to avoid ticking the actors, but you still have a cost for spawning, and it seemed like you mitigated that by recycling the quads in the example with like the birds. So is that just a static mesh where you like build all of the quads and bring that in, or is that a particle system with a very simple animation on it?
So yes, that was made by kind of pre-combining all those cards. It's usually done in Max or Maya, but I usually have a blueprint that I use that uses procedural meshes in UE4. So on a static mesh, if you check a box called Allow CPU Access, you can actually do this thing where you sample the data and just like copy it over and over again in a blueprint. So basically you make an array for vertexes or vertices, an array for triangles, and an array for UVs, and then you kind of grab the mesh, you get the data, you add it to those arrays, and then you do a loop and you just append and append. You do have to offset the indices of your index buffer. I'm forgetting what it's called exactly, but the buffer that tells you what index of the vertex you want to use. So every time you add a new mesh, you basically add the number of verts of the mesh to your offset, and you kind of recreate that array. It sounds like a great opportunity for a future blog post or something, but short of that, Pivot Painter by John Lindquist, which we use for wind effects and other things, is a great way to do that because it gives you the indices encoded, it gives you a whole bunch of other information, it can give you the center position if you really need that. So yeah, I would probably start with Pivot Painter.
Awesome. Thank you.
And I think that's probably it for the questions, so I'm going to go ahead and get off here. Thank you guys again.